Hello. Hey, good morning. Okay, so let's start the tutorial today. Today we will look at some of the questions in homework 6, and then we will also cover the remaining questions and some other questions next week. Let's start. Okay, let me see. So let's look at question 1. Question 1 asks, suppose that we have a graph G with vertex set V and edge set E. And then it is known that the maximum degree of a vertex in the graph is big M, and the minimum degree of a vertex in this graph is little m. We want to show that the value of 2 times E divided by V is bounded between the minimum degree and the maximum degree. So this is actually easy. So first of all, we recall that the total degree of a graph, if we sum up all the degrees of all the vertices, it is always equal to 2 times the number of edges. So we call this the handshaking lemma. And then we just know that each vertex has degree at least little m. So if we want to count the total degree, it must be greater than or equal to m times v. And similarly, we will have the total degree must be less than or equal to big M times V. So we combine everything together, then we will get the result. Now it turns out that the value of 2 times E divided by V, this is the total degree, this is the number of vertices, this will represent the average degree of a vertex. So the average degree would be bounded by the minimum degree and the maximum degree. So this is question 1. Question 2 says, okay, suppose that G is a simple graph with at least 2 vertices. We want to show that 2 vertices in G has the same degree. Okay, this is nothing new. We have actually studied the problem earlier when we are in the pigeonhole principle cases. So here we were talking about this question in a group of 100 people where 2 people shake hands at most once. Then there must be 2 people who shake hands the same number of times. Okay, so this is the same question as we are talking here. We are looking at a simple graph G, so that between any 2 vertices, there will be at most one edge. Okay, this edge represents whether the 2 vertices, the 2 people, shake hands or not. Okay, so if you recall how to show this question, then you will be able to show why this is true. So I will leave this for you as an exercise. Okay, the next one is we have 2 graphs below, and then we want to show whether they are bipartite or not. Now, if you want to show that they are bipartite, the easiest way is we give a particular coloring of the vertices into black and white, such that no edges are joining between vertices with the same color. And if we want to show that it is not bipartite, then we can also do something similar. We try to color the vertices into 2 colors, but then we find a contradiction. Or we can find a certain cycle that has exactly odd number of edges there. This is also another way of showing 2 graphs a graph is not bipartite. And in this example, the 2 graphs that we are seeing here, they are both bipartite. So we are just giving a coloring. So we color these 2 as white. Then we see that all the edges are joining between different colored vertices. And similarly, there's level 1, level 2, level 3. So we have the level 2 vertices are in white. So we will see that all the vertices are joining from level 1 to level 2 or level 2 to level 3. So we see that it is a bipartite graph. So this is a proof. This is a proof by construction. Okay, so we give an example coloring. Okay, we skip question 4 for now because question 5 will be helpful for proving question 4. So we want to show that for a graph G, the union of graph G and its complement. So the union of 2 graphs with the same vertex set is simply we we keep the same vertex, and then we keep all the edges in the two graphs. So we want to show that the union of graph G and its complement will be a complete graph. And then the n here represents the number of vertices in these two graphs. So first of all, we can see that the complete graph will contain every edge between any two vertices u and v. On the other hand, uv, this edge, will either appear in G or the complement of G. If it appears in G, done. Okay, if it doesn't appear in G, then it must appear in the complement of G. So in that case, for every two vertices inside the graph G and union of G bar, it will be there. So it means that this one is the same as this one. So any edge here appears here, and any edge here appears here. Okay? Now, if we know how to solve question 5, then we can go back to question 4. Question 4 tells us that suppose that G is a simple graph, and then G, it is known that G has 15 edges, and then the complement has 13 edges. We want to find out how many vertices are there in G. So we can make use of the result of question 5 directly. Suppose that n is the number of vertices in G. So by the result of question 5, we know that the union of these two graphs G and G bar will be the complete graph. But we also know that the graph G and the complement of G, they do not share any common edges. So what does that mean? So it means that it has 15 edges, it has 13 edges, and they do not share any common edges. So the number of edges in Kn is exactly 28. So Kn is a complete graph. The number of edges in a complete graph is n choose 2, because between any two vertices, we choose any two vertices, between any two of them, then is exactly one edge. So n choose 2 is 28. So by doing some computation, we will find that n is equal to 7. So here we rely on the formula of computing n choose 2, which is n times n minus 1 divided by 2. Okay, so we find the answer to be 7. Okay, so that's it. Okay, now the next question should be question 6, but then we try to show question 7 first, because it will be a little bit helpful to help us to solve question 6. So question 7 says that suppose that G and H, they are known to be isomorphic graphs. We want to show that the complements of these two, they are also isomorphic. Okay, so these two, if G and H isomorphic, then their complements are also isomorphic. The answer turns out to be super easy. Okay, remember what is meant by isomorphic graphs. So if G and H are isomorphic, then there exists a one-to-one correspondence between the vertices of G and H, such that whenever UV is an edge of G, then using the correspondence F, FU and FV will tell us, oh, this will be an edge of H. This is true if and only if. So any edge in G has a correspondence to every edge in H, and every edge in H will also have a correspondence with every edge in G. And the correspondence are done by using a consistent labeling of the vertices. So we try to relabel the vertices of G into the labels of vertices of H. Okay? Now, because this is true, this is UV in G, if and only if FU, FV in H. So UV is not in G. It must be true that it is if and only if FU, FV is not in H. Okay? Now, UV is not in H means that UV will be in G bar. FU, FV is not in H. It means that FU, FV will be in H bar. So using the same correspondence F, it will give us a correspondence between the vertices of G bar and H bar, such that UV is in G bar if and only if FU, FV is in H bar. Then this implication tells us that G bar and H bar, they are isomorphic. Okay, So this is the solution of question 7. And now we are back to question 6. So this will be the final question for today. So we want to ask, are the following two graphs, are they isomorphic? So for these two graphs, if we count the number of vertices, they are the same. If we count the number of edges, they are the same. But then is it easy to show that they are isomorphic, or is it easy to show that they are not isomorphic? Now, for these two graphs, there are so many edges. So one thing that we have just learned from question 7 is we can look at the complements instead, because the complements of the graphs may have an easier structure to identify, and then the complements of these graphs will have fewer number of edges. So as long as the complements are isomorphic, then the two graphs are isomorphic. But if the complements are not isomorphic, then these two graphs will not be isomorphic. So let's look at the complement. So what is the complement? Dong. So let's focus on the red edges. So the complement on the left-hand side, it looks like there are two disjoint squares. Okay. And the right-hand side, it looks like a star. But immediately we can see that the complement graph of the left-hand side has two connected components. But the complement of the graph on the right-hand side, there is just one connected component. So that means what? That means that the complement graph cannot be the same. Yeah, because how can two graphs be the same if one of them has exactly two connected components while the other has one connected component? It can't be true. So the two graphs, the red edges graphs on the left-hand side and the red edges graph on the right-hand side, they are not isomorphic. In that case, the original graph must not be isomorphic. Okay, so this is the end of the tutorial for today. Okay. Okay, let me see if you have any questions. Let me see. Eh? Oh, you're right. Thank you very much. So I made a mistake. So it's not 7, right? It should be 8. 8, right? So thank you very much. So yeah, I'm just too careless. So here, n choose 2 is equal to 28. So n should be 8 because 8 times 7 divided by 2 is equal to 28. Thank you very much. Thanks for pointing out the mistake. Okay, so thank you, Ethan, and thank you, Leach. Okay, so yeah, that's all for today. Okay, and then yeah, and for this week we will continue some other. So the lecture here for this week we will talk about more on the planar graphs. So there are some interesting results, and then we will have a new concept called homeomorphic as well. Okay, thanks all for coming. Okay, thank you.